Good evening, everybody. This is 7:30 at PST time. Let's get started. And the people are joining still. Okay, so how was the midterm? What's your feeling about that? Anyone wants to?
I felt like the practice prepared us pretty well.
Okay, good to know that. Good to know that. Any other comments from anyone? No? Okay. So now, after the midterm, we will kind of switch our mode of learning on this specific class. So far, if you kind of observe the pre-midterm era, we started with most of the things as a hands-on. Like we designed circuit, we designed digital circuit, sequential, combinational, try to put it on a hands-on simulation environment, look at the behavior and all this stuff. And till now, like whatever we studied till lecture 11, it has an component to your projects as an hands-on, like you are modeling the same processor and observing the behavior in a simulated environment. Now, from now on, this will be more theoretical. Like it will be beyond scope of our simulation environment and stuff like that. It is more like theoretical, more numerical analysis on, especially on the runtime performances. Uh, so be aware of that. Like we'll be switching our learning mode a little bit from more hands-on approach to more theoretical approach now. And this is like the real architecture study. We started with lecture 11, but that is more practical oriented, I would say. But now it will be like really abstract concept. You need to keep up with the pace of those all these concepts. Sometimes you'll find yourself maybe like why these things are happening, why these things have been decided. uh, Mostly because like you won't be able to visualize the whole system in details. Okay, so that's what, please be aware that it will be very abstract discussion from now onwards. I'll try to make it as practicable as possible, as practical as possible, so that you can visualize the system. And in terms of like when you program a system, different types of systems, you could be able to think how inside this system your program is being executed. Okay, that is our target goal, and that concept is very much needed, because when you go out in the industry and you assume more senior engineering positions, you need to analyze deeper details about the performances, about like it's not only runtime, it's basic also memory consumption perspective, those things. And that point, this abstract concept will come into play. If you understand them better, you can actually do better in the field as an engineer. Question so far? So our topic was, we started to discuss this lecture 12 as an instruction set architecture and some of the convention that put forward in the architecture world, like big Indian convention, little Indian convention for multi-byte data placement into the memory. Um, and this multi-byte data placement and Indian convention comes in the picture because traditionally the lowest amount of information that we would be able to access using a processor from memory is a byte. So we assume in that model every address contains one single byte. Now, from that, if you see the physical memory as an electronic component, they their addresses are word addressable. Okay, so uh, so basically, then it comes into the issues of like, how am I going to first of all place the bytes in which order? Should my lower address has the lower byte or lower address has the higher byte? That is the endianness problem. And also this mismatch of concept, like this processor thinks a memory is byte addressable device, but real electronic memory device is word addressable. For that reason, memory alignment problem comes in. Those who are my older student from CS47, you probably recall we talked about these alignment issues in detail in that class. So if you remember that, and if you in your study group you have some student who are not in my class, please like discuss these alignment things with them. Okay, so you guys have better concept on the alignment and why it is coming up and stuff like that. That's very interesting concept to grasp. But nonetheless, there is this endianness problem. There's alignment problem, not much of significant for this class. For one reason that our memory model, what we are assuming in our project is an word addressable memory, meaning that your processor also knows this is a word addressable. So if you recall in your instruction set, CS147DV, we don't have any byte addressable instruction or, sorry, byte accessing instruction or half word accessing instruction. You don't have like load byte, store byte, load half word, store half word type of instruction. We only have store word and load word, right? So in that sense, like we assumed in our inherently in our that sample architecture that memory is word addressable, so that we actually got out of first of all this this thing, your alignment issues, and we don't pay actually much attention on the endianness as well. Somewhat like we just go with whatever default the Verilog simulation system assumes, we go with that. But anyway, but in real world, these are the bigger problems to solve or assumed by a processor. Each processor actually goes with stick to one convention. Either it follows big endian or it follows a little endian. Some smart processor also has an external deep switch. You can configure that processor to follow either big endian or little endian. That's a different story, but some processor has that. But essentially, during the operation, when you power that up, the processor, it assumes one specific endianness, either big or little. And neither is wrong. Like one can assume one way or other. That's fine. So that's one thing. And then in this lecture, we also talked about this different mode of data access. Few of them have been incorporated in our CS147DB. There are much more variety, even beyond what we have discussed. Like it's really a lot of different style of data access possible. In this lecture, we have just discussed a few of them, like, and only out of them, only few of them even used on our CS147DB instruction architecture. But you need to be very clear about the concept of this data access and different mode. Also, we talked, then we went into some class of design like CISC, complex instruction set computer, and reduced instruction set computer. That kind of architecture comparison, like, and what's their, why they have been developed in that way, why there are two school of this thought, CISC versus RISC, and it has been a debate for many, many, many years. Like some people think RISC is better, some people CISC is better. If you ask me my personal opinion, I think it is actually depending on your application field of the processor. So if you are targeting for one typical market versus the other, you might want to choose between one style with the other. And frankly speaking, like modern processor, in the modern processor, these classification are even blurrier. Like it's really like for example, like Intel always claims they are CS architecture. They have this huge set of assembly instruction it supports in the processor. I believe internally they are actually some sort of risk processing they've done internally. Otherwise, they couldn't have done much more pipelining and all this stuff. Uh, so that's the things I wanted to bring up here. Though we classically discuss this risk versus risk in the computer architecture classes, but modern processor actually is kind of mixed. Is whatever applicable to the target market for that processor. That's they go for. Question? Let me see if you guys raised any question on the canvas. Discussion. I don't see anything there. So anyway, hopefully you guys have understood that this lecture okay. Then what we can do, we can actually do some problem as a group. Let me see. Okay, I'm sharing my whiteboard with you guys. Okay. And now let's solve two problems as a group. So number one is something like this. Okay, and next one be something like this. And I need to give you a picture of the memory. Okay. Okay, so first problem is that following the bytes, this list of bytes, excuse me, yeah, this list of bytes have been placed from this address, let's say. Now we need to find out what is the full word accessed from the memory location this in a big endian and also in a little endian convention. So this is like an easier side of the problem. The next one involved little bit detail. Assume that microprocessor is a little endian data access convention while accessing 32-bit byte addressable memory. Also assume there is no issue of data alignment upon data access. All values are in 32-bit 2's complement form. If this computing system is presented with the following snapshot of the memory. So this is my memory snapshot. Okay, so this is like starting from a lower address of 10000000 till 000C. And you have this byte data stored there on those addresses, let's say. And then I have this 32 register snapshot, the values like register and the corresponding value in the hex format stored in that. So what we need to do, like we need to exercise our understanding of different different data access process, like a direct read from the memory location this, right? Like it's a 4 byte, always assume this is the 4 byte. Then an indirect read from the memory location this, what would be that result? A register indirect read from the register 4 and a displacement read from register 6 with displacement of this amount. Okay, so with this 4, let us open up the breakout room for maybe 15 minutes, maybe 15 minutes. Let me see. Okay, breakout rooms. I see that there are some groups with 1 people. I will move them around. Okay. Let me first assign this thing while you guys can look at this problem individually and see. Let me just put around, rearrange the rooms, and I'll open it up. Okay, I have redistributed the population. Now I'm opening up this breakout room for 15 minutes.
to a breakout room.
Oh, okay. Which one is your study group? Do you remember, Isita?
I do not. I believe it's probably 6, but I'm okay with whatever group.
Okay, just hold on. Okay, let me resume the recording first. Okay, so let's see. How about group one for that problem one? Have you guys come up with a solution on that? And can you explain? Group one is Hyder, Laura, Matthew, those three.
Yeah, we came up with a solution, we think.
Okay,
You want me to share a screen or something?
sure, please.
Okay, sure. What can you see? Anything? Here we go. This is what I have. So we have the memory, we drew it. So we're assuming that this was like, is it byte addressable?
Mm-hmm.
Yeah, okay. So then like if this was your memory inputting everything, then it would just be like 2 hex values per group
Okay.
in the order that you entered them. So like going up from 0, 0. And then if you're trying to do little endian, then the location that you're given in memory. So in our case, I think it was 004, right? So you would use this as your LSB and then take 32 bits worth of data and then use the other one as like MSB. So that's what we did here. This is the
So the LSB is what ultimately?
LSB would be 0x56, right?
LSB for the little endian.
Little endian, yes, little endian.
Okay,
And then the
endian.
MSB would be
Right.
0x89.
Mhm.
Okay,
So
and then okay, go ahead.
little endian. Okay, so that's what you marked as LE as a little endian, which is 8, 9. Okay, 8, 9, 7, 8, 6, 7. Yeah, and 5, 6,
Sorry.
7, 8, 9, 7, 8, 6, 7, 5, 6 seems like correct. And big endian would be like a lower address would be the MSB.
Yeah.
5, 6.
Yeah.
Yeah. Okay, this seems correct. Thank you
Just
very much.
messy. No
Yes.
problem.
So everyone got it? Any question for Matthew or others?
Is the question asking for a double word or a single word for data size?
It's a single word.
Isn't a single word 16 bits?
The single word is 32-bit. In this class, we assume single word is 32-bit. Half word is 16-bit.
Okay, thank you.
Okay. Then the next one, how about group number 2? Is Mr. De La Cruz, Alan Viola, Max Wong. Group number 2, did you guys tried it, came up with a solution? No, no one is going to answer that. Okay.
I'm sorry, which group did you?
Group number 2, Mr. De La Cruz, Viola, and Wong. Right? Group number 2 is there. No, none of you want to volunteer on this? Okay, how about group number 12? Hang Ho, Logan Joven, Medina Arola.
I'm sorry, I couldn't solve it. So sorry about this.
Okay, no problem. Okay. Okay, who wants to volunteer for this one? Number 2. Okay, then let me try. Share screen. Okay, so here we are. We have this information, right? What is our memory content and what is our register content, and from that, our first one is to have a direct address from the location 100, right? And we are talking about the little endian, right? Little endian. So let us mark this little endian data access. And as Matthew told, that little endian would be lower address is the lower significant byte, and we are reading from this address, right? So that means we are reading these 4 byte. We're assuming this is a word, full word access. Direct mean from that address, we are just picking up that data and using that as an data, basically that information. So that means essentially for A, it will be 0x10 00 0004. Now the B, question number B says that is the indirect read from this location. So what happens, indirect read from this memory location, that mode, this memory location is first read in, and use that as the memory address for the data. Okay, so this is whoever is programmed in the C++ area, it's a pointer. Basically, we're talking about a pointer. So this one now read from this address. That's the indirect. And that means ultimately my data will be picked up these 4 byte. And my answer, then it's a little endian system. So B would be 28A456B6. Now the next one, number C. C is a register indirect read from the register R4. So what is that? Means the system will read the content of this register and access that memory. So it will be reading from this guy. So use that as an address, that value, and have 4 byte value. So that means my answer for C would be 2EEBC3A5. All right. Now the last but not the least is a displacement read from register R6 with a displacement value this. So this displacement value, okay, this is like an 2's complement system, right? So essentially FFE means, I believe it is -2. Let me just check. Okay. Yep. Okay, this is -2. So this one is -2. That essentially means that you read from the register 6, which is this one, okay, and add -2 on top of that. Means basically you are subtracting 2 out of that address. So it will be AP A it will be 9. Okay, it will be 9, right? So this is, we're computing 0, 1, 0, 0, 0, 0, 0, 0, b, x minus 2. So which is like, let me just try that out. 1, 0, oops. 1, 0, 0, 0, 0, 0, 0, b minus 2. Yeah, 1009. Okay, 0, 1, 0, 0, 0, 0, 0, 0, 9. So this is my resultant address from where we are trying to access. So this is the address we are trying to access, and it will be again 4 byte. So my answer for D would be sorry, not C3, 132E EBC3. Make sense, everybody?
So,
yeah.
For part B, the indirect read, that's basically the one that has an offset such that instead of reading from 1000, it reads 8 positions later, and that's why it's reading at 1007. Or am I reading
1007? Oh, no. This is, okay, the B, number B, this one, right? So
yes.
it is first reading from this memory location, okay? This memory location. So what it is reading this 4 byte, right? Now it is constructing that 4 byte data, which is like little endian position 1, 0, 0, 0, 0, 0, 0, 0, 4. Now since it is an indirect read from the memory location, okay, then it will do another reading from the memory. So using this guy as an address now, pick up this value and use that as a value to be ready.
Okay, I see it. Thank you so much.
Yeah, it's an indirect read. So indirect read involve like 2 memory access. First is access from that memory to pick up an address, and then that address will be ready. By any chance, did you program with C, Yorick? Anyway, that doesn't matter. Like whoever has programmed with C, this is like very fundamental and very strong concept of pointer. And many things can go wrong if not used correctly. So, but this is more like a pointer access from one location to another.
Professor.
Anyway. Yes, Matthew, did you?
Yeah. I'm wondering, you have a fast method for converting 32-bit 2's comp into like decimal, or like without the calculator, I guess, or something like that.
Yeah, that's that's that you can do. That's a good question. Let's say this one, right? This one is like, you can pretty much say these are the F are all 1, right? Etc. etc. So 2's complement, you basically want to inverse the first, negate the bit value. So it will be like if you do a negation of these pattern, it will be something like 0, 0, 0, 0, 0, 0. So last one is basically is important, is E, right? FE. E would be 0, 0, 0, 1 if you negate that, okay? And you add 1 top of this. So ultimately your value is 1, 0, which is 2.
Okay. Yeah, that makes sense. Because it's F, right? Because you know that they're all ones, but if it was like a mix of,
If it is a
you
mix
know,
up, then
yeah,
it's a bit
it's a
difficult.
little harder. Yeah, okay.
I would recommend use calculator,
Yeah, yeah,
the
yeah.
programmer's
Thank you.
calculator to do that.
Thank you.
Okay. All right. Okay, anything else? Any other question? Everyone is clear on this? Okay, then maybe we can just stop tonight early to start our spring break. I think most of you are looking for that for your finishing of the project too. But anyway, it was not meant for that. But it's up to you. Any question? Anything like on projects, on other topics? No? No one? Everyone is ready to start spring break early, seems like. All right, see you in maybe in like 2 weeks, right? Like next week is all closed, all break, and then we'll come back to on April 6th. We'll see you on April 6th. Have a very good and nice spring break, everyone.
Thanks, Professor. You too.
Thank
Thanks so
you.
much.
Break.